Once we know our population size, we can move on to studying how populations grow over time. So to do this, we are going to use sort of a general calculation here. This is an equation that connects the number of individuals with the reproductive rate. And it allows us to calculate a future population size. So let's start with the variables that are here. N is always going to be the population size. And T is always going to represent time. R, or sometimes little r, is going to be the reproductive rate. We'll also call this the growth rate of the population. This is a generic formula, which is why it has a big R. We're generally going to use little r for this equation. N at time t is basically going to be generation 0, or you could also think of this as generation 1. It doesn't matter too much. And then this little 0 on the R is just telling you the reproductive rate at the start. Population size at t plus 1 is going to be for the next generation. So if we're calling the first one generation 0, the second one would be generation 1, generation 2, and so on. So we are going to talk about how we use this equation. We're going to change it a little bit as we go on to talk about different types of growth that a population might have. But this just tells us that our growth rate, or the change in the population size, depends on two things. It depends on the population size, and it depends on the reproductive rate. So both of those are going to affect how quickly or slowly a population grows. For example, if we use beavers again, because we started out with our life history of beavers, if we want to predict the number of individuals in the next generation, we're going to take our current number of individuals times their reproductive rate. So our number of individuals in the next generation is going to be equal to the current population times their reproductive rate. So N at generation 1, or time 1, is going to equal 1,100. So we can see here that the population has grown because we have increased from 1,000 to 1,100. And we can also recognize that our reproductive rate is positive. So it might be growing slowly, but it is, in fact, growing each generation. Now, what this doesn't tell us is how it's growing. So this could be because there's a high reproductive rate. It could be because there's a low death rate. R0 is actually a net rate. This means that we're taking the net from the births minus the deaths. So some of those deaths cancel out the growth. When we're looking at how populations grow, there are two basic models that show how populations are growing over time. And they are based on whether or not there are particular resources that are limited in their environment. The first is exponential growth. So exponential growth happens when resources are unlimited. There's no pressures on this population to keep them from growing. So when this happens, they're going to grow really, really quickly. And they are just going to continue essentially forever. As you can probably imagine, this is not very common in a natural environment, because in a natural environment, something is probably going to start limiting them. Something's going to kick in. They're going to use up a resource. That could be water, it could be food, it could be space. Stuff like waste accumulation, lack of breeding grounds, things like that. Something is going to eventually limit how quickly a population can grow. When that happens, we get logistic growth. So logistic growth is the type of growth in a population that happens when resources are limited. And so if you think about these, with logistic growth, we have to eventually have a rate that slows, because slowly a resource is going to start limiting the population. So we can look at the growth rate of a population. Rate is always some sort of change over time. So we can look at the growth rate of a population, or the change in the population size over time. And this is going to be determined by the net reproduction. So net reproduction is, again, going to be births minus deaths. So this makes sense, right? Our population is going to change by the number that are born and by the number that die. So when we're looking at these equations for growth rate, we do need to keep in mind if we are looking at raw numbers. So here we've got actual numbers of births and deaths, or if we are looking at a rate, or a per capita rate, meaning per individual rate. So here we just have a flat rate, number of births minus number of deaths. So a minute ago we did that beaver example, and we saw that our population increased by 100 individuals. We could have figured this out by maybe we had 200 births and 100 deaths. And so we can make a direct calculation that, well, we did add 200, but we also lost 100. So our population has changed by a net 100 individuals. We can also look at birth rate and death rate. So on this slide, we have a simple problem. We have a population of 1,000 rabbits, and it gives us a number of births and a number of deaths. So these are raw values. So using our equation here, the change in our population, so change in N, is going to be equal to the number of births, 100, minus the number of deaths, which is 50. So our population, our change in our population is going to be 50. And so our change in our population size from one generation to the next is going to be 1,000 plus 50. So our new population size, our population size at the next generation is going to be 1,050. But we can also use this information to give us the per capita growth rate. So per each individual, how many births and how many deaths. And remember, anytime we're calculating a rate, this is going to be something divided by something else. So if we're looking for a birth rate, it's going to be number of births divided by total population. Death rate's going to be the same thing, number of deaths divided by total population. So to do this this example here, the birth rate is going to be 100 per 1,000 individuals. The death rate is going to be 50 per 1,000 individuals. So our birth rate is going to be 0.1. Our death rate is going to be 0.05. Notice here we have our raw number births and deaths as capital letters. So our 100 was a capital B, 50 was a capital D. Our rates are always lowercase. And so if you are given a rate, it's going to work for the lowercase variable. So our raw number is going to be the uppercase, and our rate is always going to be the lowercase. So on the previous slide, we calculated our birth rate and our death rate. So our change, our per capita growth rate, is going to be the effect that our birth rate and our death rate have on our population size. So previously we calculated our birth rate was 0.1, our death rate was 0.5. And we can use this to determine our per capita growth rate. Now you may notice that we've added a little notation here. What's happening here is that our textbook is going through and actually deriving a formula, but I'm sort of skimming over it. So what we had initially was our population size, and I was calling this a change in population size. Your textbook is now giving us this notation dn over dt, and that dn over dt is essentially a calculus notation that we'll talk about in just a second, but it is just another way to say a change over time. So there's a couple of ways that we can calculate this change over time. So we can essentially calculate the change in the population as equal to the birth rate minus the death rate. So the effect of the births on population size, effect of deaths on population size. So that is shown down here along the bottom. I'm going to go ahead and rewrite it out. Our birth rate is 0.01 times 1,000 minus our death rate 0.05 times 1,000. And what that's going to do is tell us how many individuals are born and how many individuals die. And that, again, will tell us our change in the population. So if we calculate this out, this is going to be 100 minus 50, which is exactly what we got over here on the previous slide. So this is just another way we can calculate directly with number of births, or we can calculate indirectly with our rates, our birth rate and our death rate. Just to make things a little bit more complicated, we're going to look at one other way to calculate this birth and death rate. So instead of calculating number of births and number of deaths based on the rate, we can lump them all into one, and we can calculate this R value. And what we're doing here is calculating an instantaneous growth rate. So this notation that I said was a calculus notation, this is going to be our instantaneous growth. And honestly, you do not need to know how you get the math, how you do the math to get to this derivative. You don't have to have taken calculus. All you have to understand is that dn over dt is the equivalent of change in population over time. So this is going to represent our change in our population. I know the notation changed. Again, if you are worried about this, you can come see me in office hours, or you can read through the textbook. You don't have to know how this was derived. You just have to know what that means. So what we can do here is we can calculate our little r. So our little r is going to be the population growth rate. The growth rate for the current population. And this is how we're going to get our change in our population, because remember, this dn dt is our change in our population. And if you think back to that very first slide we went to in this video, the change in the population was based on our population size and the rate. So our rate is going to be our overall rate, our net reproductive rate is going to be the birth rate minus the death rate. So R is going to be that 0.1 that we already calculated minus 0.05. So R is going to be 0.05. So that is written out over here. This should be an equals, I'm sorry. Our rate is going to be 0.1 minus 0.5. So R is going to be 0.05 times N, our population size, which is 1,000, which is going to give us 50. So again, our change in our population is 50. So we've now done this 3 different ways depending on what information we're given. So we can, for this population, we can do our change in population size based on the raw number of births and deaths. We can base our population size on the rate of births and the rate of deaths. Or we can shorten that and base it just on the rate, which is derived from those births and deaths. So if you need to watch this one more time, that's absolutely fine. Feel free to watch it again, and feel free to come to office hours if you have questions on all of this math.